Okay, welcome to our free prep hour for March 30th, 2022. I'm Dmitry, coming in from San Diego. Today's theme is all about inequalities. So we're going to do a lot of moves that you may or may not know how to do, may or may not be comfortable doing, and a lot of things that I think that when we're first studying, and I remember some of this myself, maybe we understand and we basically have, but we feel a little insecure or uncertain about. So I want to create more certainty for you on some of these problems and know, where to do these moves and where not to do them. If you want other free options, you can check out one of our classes or a sample of our Interact program. Let's take a look. So basic idea of inequalities is they're a lot like equations, but we have some restrictions. And because we have restrictions, we often see people getting a little bit intimidated and not being able to say quite what they know about a particular situation. So let's run through some variations. Let's start with just a simple two-ended inequality. I've got 5 is less than A is less than 7. So in this case, what do we know about A more than this? For instance, can I pin down what A is? Do I know from this what the value of A is? Right, I don't know for sure. A lot of people, sometimes I have students who are very quant heavy, they're engineers or something, and they know very well that we can't assume variables are integers unless the question says so. But sometimes in the heat of a problem, they're in the middle of doing a lot of data sufficiency. In isolation, they wouldn't do it. But in the heat of a problem, they'll suddenly say, oh yeah, we know A is 6. It's similar to how, if I see something like this, x to the 5th minus x to the 4th, I know very well that does not equal x to the 1. I know that. In fact, it's much closer to x to the 5th than it is to x to the 1, right? Because it's 5 powers of x. Imagine x is 10. That's like 100,000. Minus just 4, which is would be 1 over x times that, like maybe 10,000. So it's the x to the 4th, because it's exponentially smaller, it barely makes a difference. But people will do this in the heat of the moment, even though they know better, right? So same with integer constraints. Sometimes people will assume them, other times people will overlook them. So if the statement, if the question doesn't specify that the variable is an integer, the only way you would know is that if we're measuring something that isn't going to be fractional. We're not going to have half a person or a third of a marble or something like that. Sometimes it could even be days. I suppose in theory, someone could work for, 4.5 days. But if they say something like, how many days this month was Peter home sick or something like that, then we're probably not going to be counting that he was home 8.5 days. We're going to say on which days. And so often they'll specify things in such a way that you can assume things are integers. And in those cases, of course, you would know that A equals 6. And that's the kind of thing we really have to watch. It could also be the kind of thing that maybe A represents the median of an odd set, right? So for instance, what if I said, A is the median, not income, I guess an income could be a non-integer, right? But the median number of followers for an Instagram page or something like that. In that case, a number of followers has to be an integer, and then maybe I'd know something about it, right? Oh, okay, maybe I know that the particular person in question has more than 5 and fewer than 7. I guess if you have an Instagram page, you ought to have more than 5 followers, but sometimes we're just getting started. So this kind of thing. Sometimes we have situations where we might be able to solve when we don't realize it. So one variation on that same kind of problem would be something like this. Okay, oops, I put the wrong variable there, sorry. Mina has S siblings, we'll call that, redo that, I think I wrote it as A somewhere else, so she's gonna have A siblings. I always like when the letters stand for the right thing, but the GMAT does sometimes mess with us there and say, say a variable that doesn't make any sense or try to trick us. They'll say, product X sells for Q dollars or something like that. I don't know why they don't just say X dollars, because they like to frustrate us. All right. Oh, sorry. So yeah, I'm not doing that right. Okay. So in this case, we have an inequality that might at first glance appear to give us nothing. And when I see people do a problem that can be translated to this, or where, they'd have to do some work to get here, a lot of times people say, oh, there's lots of values. So in a data sufficiency setting, someone might say, oh, well, clearly there are a lot of possible values for A. But when we actually try to do it, we get another story, right? Because we have, first off, can't be that large a range because 112 and 115 aren't very far apart. And so then if we start running in there, we can say, oh, let's see, I can take the 90 away from both sides. So I got 22 and 25. And then I can divide 4 on both sides. So at this point, do I know what A is? I can look at the ends and sort of say, hey, I've got this sort of pinch. Yeah, we have to do some quant for sure, right? It's got to be 6, right? So why? Because 25/4 is a funny fraction, but I know what it's more and less than, right? I know that 24/4 is 6. 25/4 is a little more than 6. Another way to say it is that 28/4 is 7. So this is less than 7. Whereas 20/4 would be 5, 24/4 would be 6. So we have this pinned down. And so you could call this sort of a pincer move, right? And the pincer would be when I'm, it seems like there are a lot of possible values, and then when you really pin it down, there's only one. You may have this sometimes when you think you have a lot of time off. You think, oh, I'm not busy at all tomorrow, so anytime you want to have a call, I can do it. And then you say, oh, well, no, because I'm going out to there. No, and then I have this, and that would be, oh, okay. And if we start there, then okay, I could talk at 2 o'clock. Suddenly you're much more constrained than you realize. And we can have things like this too. And this is where data sufficiency really messes with our minds, because we'll just look at something in a glance and say, oh, there are lots of possibilities. To which I always say, great, name 2. The most important thing you can do to get really accurate on data sufficiency is, if it seems like something's insufficient because there's more than one value, you should be able to name them. If that's easy to do, that it's no trouble. And if it's hard to do, that could be because there's only one value. Right. So if I say something, imagine it was something silly like they tell us, A is greater than 10. I keep doing the S. Sorry about that. So if they say A is greater than 10, then of course there are lots of possible values of A, right? But I can easily name 2. I can say, all right, well, A equals 11 or A equals 12, right? And so I don't have to write that down on my paper, but I can identify them. If they give me something that's less clear, then it might be useful to say, well, let's see, A could be, 11, could it be, no, it can't be 12. What else is there? And that's a lot of times where people catch their errors. In class, I kind of, get stern with folks when they jump to say something's insufficient, where there's definitely only one answer. And I say that not because I want to punish anyone who made a mistake, but a lot of people, they never made a mistake because they didn't actually try to do it. In other words, they didn't say, oh, let's see, the value could be this. Now, what other value can I get? And if you haven't done that, don't rule something insufficient, right? Always make yourself do that before you say something's insufficient. Okay, let's look at some other moves. Sorry about the variable confusion there. There's just one variable in this question. Okay, now here's a question with multiple variables. And it's a kind of question you'll get asked in data sufficiency. So if AB is greater than AC, is B greater than C? Okay, so what do we think about this? Do we know the answer to this? Is B greater than C? Now, when you say no, do you mean it's definitely not, like it's less than or equal to C? Or do you mean, no, we don't know if B is greater than C? Okay, I'm seeing, yeah, rephrase this, right? Depends on the sign of A, right? And this is another move that we might do in a hurry. Certainly, if we're told the sign of A, then this would be sufficient information. If they tell us A is positive, then I can divide both sides by A and I get B is greater than C. And if they tell us A is negative, I can still divide both sides by A. I just have to flip the side and I get the B is less than C. That would still be sufficient to answer the question. It would give me a no instead of yes. Those both can't be true, but of course, A can't also be both positive and negative at the same time. So if they told us either one of those, that would be sufficient. Without knowing the sign of A, I'm stuck, right? I don't know, right? If A is positive, B is bigger than C. If A is negative, B is less than C. Now, follow-up question, could any of these variables, A, B, and C, that's what I was gonna ask, right? Thank you. Could any of these variables be equal to 0? So take a moment to think about each variable in turn. Could A be 0? Could B be 0? Could C be 0? Because we have cases written out for A is positive or A is negative. We don't have any cases written out for A is 0. Is that a mistake? Yeah, right. We can't have A is 0 because then both sides would be 0. All right. So imagine A is 0. You'd have 0 is greater than 0. That's not a thing. If it's a greater than or equal to, that would be another story, right? Because of course 0 is greater than or equal to 0. It's equal, right? But I can't say 0 is 0. So I can say, all right, not A, since then this two sides would be equal. So our cases still hold. If A is positive, we have one result, and if A is negative, we get another result. In that case, could B or C be 0? Yeah, right. If B is greater than C, then we could have either of them really be 0, right? Because B could be 0 and C could be negative. And so in this case, like we have that we could have B 0, C would be negative, or we could have B is positive and C equals 0, right? Or negative, of course. If B is negative, then C can't be 0 because it wouldn't be less, but C could also be negative, right? So we have some different cases there. If B is less than C, it just flips the other way, right? We'd have the same kind of thing, right? So C could be 0 and B could be negative, or B could be 0 and C could be positive, right? Okay. So what this gets to, by the way, now that we're testing all these different cases, is one of the things that I want to caution people about, especially if they've studied a lot of our material. We spend a lot of time in our material and in our course, our books, and I think rightly so, pushing the idea of picking smart numbers and testing cases. Folks who really are comfortable with algebra sometimes have to be convinced, against their own better judgment to do that. And I think it is a good thing to do, even for people who are strong in algebra. If you're one of those people who just tosses off a quant 50 without any trouble, then maybe not, right? Maybe you don't need it. Although some of us who are getting those kind of scores are still picking numbers a good amount of the time. And then folks who don't love algebra as much, maybe they take less persuading. Hey, picking numbers is great. However, I want to suggest that on inequalities problems, picking numbers can be a bit of a nightmare, especially when there are multiple variables. And so one of the things you see here is that just figure out the positives and negatives is enough trouble. If I then start assigning values to these, saying, okay, let's see, if B is 0, C could be -3, or if B is 5, then C, okay, C could be 2, or it could be 0. There's too many things. I think adding specific values makes these more complicated. And sometimes we want to prove things algebraically. There are a lot of cases where we might pick numbers because we're dealing with less than or greater than. We might pick numbers that either don't put us over the threshold we want or take us too far away from a particular threshold, so they don't allow us to easily test the limits. If you are going to pick numbers, you might want to pick numbers right at the limit and then far from the limit. Like if I know that B is greater than 0, maybe I want to pick a very small number, like 1/3 or 1/10, and then a large number like 20. Sometimes I'll even test the value itself, even though it's excluded. So if I say B is greater than 0, I might say, well, what happens if B is 0? And then go from there just to get an idea. But a lot of the time on inequalities, I will avoid picking numbers. And you'll see cases like this where picking numbers just seems to make things a little harder. Okay. Although, of course, I've set this up as not as something to solve, just as something to look at. Okay. What about this one? Another case. If a squared is less than or equal to 25, what are all the possible values of a? I think folks here, if you've been practicing for all, will know how to do this. I just want to look at some variations of it. If this is something, if you're watching this on the video, you might need to pause a minute and play with this. What result do you get here? What's the range of values we can have for a? Yeah, anywhere from 5 to -5. And since it's a less than or equal, we'll include those ends, right? So when you're unsquaring something, you have to think about positive and negative solutions. When it's an equal sign, it's simple. It's just plus or minus that thing. When it's an inequality, we have a few other things to consider. We have to consider direction. And generally speaking, the direction simply flips. If you want to be very technical about it, I'm not saying you should do this, but you can. You could say, I've got two possibilities. One is that A is positive or 0. It's not 0. Well, it could be 0. One is that A is positive or 0. And the other is that A is negative. When you unsquare a square term that was positive or 0, you just get the same thing. So in other words, if A squared is 25, and I'm putting equal instead of less than for a reason, then I would just say A is 5, right? If A is negative, then when you have A squared is 25, then technically, if you want, you could say that negative A is 5, and therefore A is -5. But most of us at some point sort of memorize that you can just flip that negative sign to the other side. Now, when you do that within an inequality, you have an extra step. And the extra step comes in that if we say, okay, A squared is greater than 25, when I unsquare it, I'm saying A is greater than 5. That's straightforward, I hope. But here, if I say A squared is greater than 25, the interim step would be to say, okay, if A is negative, that means when we squared it, we reversed its sign. So A is negative, and it's really negative A that's greater than 5. And then we flip the sign and move that negative. A is less than -5. Now, again, that is something that over time you just might memorize, or maybe already have memorized. But if you want, you can do it out and put the negative on this side. But a lot of us just will find it easier, especially if there's a large amount. Imagine something like I have, 15A plus 43B minus 12 squared equals 25. It might be really nice for me to be able to say, oh, 15A, the negative case of this, if all of this, not necessarily A or B, but the whole term is negative, then it would be this equals -5, right? And not have to run that negative through all the terms. Okay, so these would be the two possibilities. And what this ends up going into, here we have the less than or equal, so I'll add that in. What this ends up turning into is a nice conjunction in the middle. And so I'll draw that. We would just say, okay, this is all the values from 5 to -5. So we can see that that's what we get when we have a less than or equal. What would happen if we had a greater than or equal? For instance, what if I had A squared is greater than 10? Then what would be the possible values of A? Generally speaking, when you have a greater than sign, what you're going to get is you're going to get a disjunction. You're going to get things pointing off into infinity another way. And what I'm hoping, even if you know how to do this, or if you figured this was true, I think it's good to sort of have this fit and make sense. which is that when I'm saying a is less than some value, I'm really limiting what a can be in terms of its absolute value. Another way to say that a squared is less than or equal to 25 is to say the absolute value of a is less than 5. If you square root, in fact, good thing to know in general is that when you square root an a squared, and specifically if you put a radical sign in math land, sometimes when you say the word square root, you can be talking about a negative root. When you draw a radical, you're never talking about a negative root, you're talking about a positive root. So radical a squared is actually the same thing as absolute value. So we're saying the absolute value of a is less than or equal to 5. And so we're limiting how big a can be, either in the positive direction or in the negative direction. But when we have a greater than, we're having the opposite. We're saying, hey, it could be all sorts of things. If your income squared is greater than 10, you don't have to have a small income. You could be making $50 million. It's just more than that limit, right? So when you can get used to the idea that when you have a less than for a squared term or absolute value, you're going to have some conjunction in the middle that usually runs together. Whereas when you have a greater than, you're going to have a disjunction that kind of splits apart into two. It's going to be an or situation. You're going to say, hey, either a is greater than root 3 or a is less than negative root 3, right? And since it's symmetrical here, we're just squaring a. There's nothing added or subtracted inside there. We can draw that in. So that would look something like, I'd have to draw. So root 3 is about what? Why did I put root 3? Sorry, a few errors in the slides today. Let's try that again. I think what I intended was that it's around 3, which is what I was about to draw. And I was like, wait, root 3 is not. So let's try that again. So greater than root 10 or less than negative root 10. Thanks to those who are pointing it out. Yeah. So here, let me draw this and I'll get to the question you're asking. So when I draw this in, then I'd be saying, okay, root 10 is just a little over 3. If I had done root 3, that's about 1.7, right? But so we're gonna be a little over 3 and we're gonna expand outward forever, right? This could be as big as we want, right? And then similarly in the other direction, I'd say, okay, and negative root 10 is gonna be a little more than 3, a little less than negative root 3, since root 9 is 3. So we're going to be like that. Okay, so that would be our disjunction here. Similarly, if they had said greater than 25 here, we'd have, instead of that black arrow, we'd say, okay, it's going to be bigger than 5 this way, or it's going to be less than negative 5 that way if we'd had a greater than. So the question was about square root versus radical. The basic idea is, when we talk about a radical sign, we're talking about a positive root. When we ask what's the square root of 25, usually we're still talking about a positive root. In actual math, we can have, you could argue that the square roots of 25 are 5 and negative 5, but that's not usually what they're asking about in the GMAT. But the main difference is that when I have an a squared, I'm squaring something that's unspecified to get to 25, and so you don't know if it's a positive or negative thing. Where if I'm asking for the root or the positive root, then I'm referring to the positive number that when squared gets 25. So that's what it is. This isn't something that's going to get tested a lot, except that you have to know that there's an underlying, if there's an underlying unknown, like an a squared or x squared, you just don't want to assume that that thing is positive. But we won't generally, radical signs will always mean positive roots. Usually when we talk about a square root, we are talking about a positive root, and we're not going to take square roots of negative numbers, thankfully. No I on the GMAT. But we can have the situation where we're taking the square root of a squared variable, and then it could be positive or negative. That's right, 25, yeah, 25 can be 5 squared or negative 5 squared. So it is true that 25 does have 2 roots, and I'm not saying it doesn't. I'm not asserting that. If I were to ask you what's the square root of 25, I might expect you to say 5, because that's what we normally think of it as the positive version. But yes, technically that is true. Just like technically, among the factors of 10 are -2 and -5. But usually when we're listing factors of 10, we're looking at positive factors. So that's more of a convention thing. The GMAT's not going to test whether roots are always positive or not. It's going to specify what it wants from you. But if you have a squared term that's not talking about a root, then you don't know if that squared term is positive or negative. Okay. So a related thing, as I said, is absolute value. And sometimes what you'll have is you'll have something throwing you off a little bit inside your absolute value. So how would we draw this one out? If I'm going to do absolute value of n minus 2 is less than 5, this is something that a lot of folks have done and they might get right, but they have to stop and think about it a lot. So it might be useful to get sort of a mechanical way of thinking about this a little bit more. So what do I do to solve this? Couple of things I can do. One is to keep in mind that anytime I am dealing with an absolute value, there are two possibilities. One is that the underlying thing that I'm being asked about was already non-negative, was already positive or potentially zero. Okay. In that case, I can just take the absolute value off, it doesn't matter, right? If I told you the absolute value of my age was more than 20, you say, okay, well, I know you're not zero, and I know your age isn't negative, or zero actually would change anything anyway. So I know you're not a negative age, so you're just saying you're older than 20. That doesn't mean anything special, right? The absolute value of my number of siblings is more than one. Okay, it's just, I have more than one sibling. There's no negative number to worry about. In a case where the underlying thing could be negative, then I have to think, well, what does absolute value do? Absolute value turns negative numbers positive, right? But how does it do that? It multiplies them through by a negative. So a very mechanical way you can do any absolute value question is simply to look at the two cases and say, all right, one case, I don't have a negative, I just remove the absolute value sign. So what that looks like is, what that looks like is I write, okay, just n minus 2 is less than 5. And now I'll just manipulate this the way I'd manipulate any inequality, n is less than 7, okay? The other possibility is I have a negative case, in which case I'd say n minus 2 is greater than negative 5. And what a lot of us will do is flip that, right? Instead of writing the interim step. So I guess what I'm saying is I could have initially written negative of n minus 2 is less than 5. And I think then you could do, multiply through by a negative and get this. But if I don't need this step, I'll just jump here. I'll just say, okay, when I'm doing the negative case, I flip the sign and flip the value of the piece on the right. Okay. And then I'd add 2 to both sides, I'd get n is negative 3. So this is one way I could do it. And again, because it's a less than, nothing changed from last time. Well, less than is going to give me a conjunction. It's going to give me a situation where the values join in the middle. Any value between 7 and negative 3 exclusive will put me less than 5, right? When n is 7, 7 minus 2 is 5, so I need n to be a little less than 7. N gets down to 4, 4 minus 2 is just 2, n gets down to 0, 0 minus 2, now it's a negative value inside. N was positive, but n minus 2 is now negative. Absolute value of negative 2 is positive 2, we're still fine. It's once we get to n being negative 3, we take away 2 more, it's a negative 5, that turns to 5, that puts our limits. The question was about the vertical signs. That's absolute value, and that's what we're dealing with here. So the vertical lines mean absolute value. Technically, that means distance from 0 or absolute distance between the two things. So for instance, if I said like, I don't know, let's say my friend is a foot shorter than me. I could say that my height minus hers is 1. I could say her height minus 9 is technically negative 1. Absolute value of the difference says I don't care who's taller, it doesn't matter. It's just a foot of difference between us, right? So it's saying the absolute amount of the difference between n and 2. N might be 3 more than 2, 3 less, but it's within 5 of 2. That's what absolute value is. It's not like parentheses at all. Parentheses just set things aside. Absolute value do set them aside, but it's saying, hey, leave this alone if it's positive or 0, but flip the sign if it's negative, make it positive. So one way people initially learn absolute values is to say it makes stuff positive, it makes negatives positives, and you can learn it that way as well. Another way we can get used to doing this is graphically. If you think back to the what we did before with the less than 5, what we had said was, hey, if the absolute value of something, let's say the absolute value of, or I'll use the variable we used before, A. If the absolute value of A is less than 5, then on the number line, I can fill in and say anywhere from -5 all the way up to 5, A can be. Now, what am I doing with this -2 piece? Well, I'm offsetting it, right? My number n can be bigger than A can be because it only has to be less than 5 once I take 2 away. And so n could be, say, 6, because when I take 2 away, still less than 5. Whereas on the negative side, it restricts n further in how much it can go, because if n were -5, and then it took 2 more away, now it's -7, it's too far. And so what you'll see, and you can do this kind of graphically, is you can say, all right, if normally my graph would be this, the strange thing is that subtracting 2, and you'll see this with a lot of functions, quadratics and things, is that now it shifts everything over by 2, right? These are exclusives. You want to be precise, right? It's like this. We're saying, okay, taking the normal line I have, I'm going to shift it over by 2. Instead of going from -5 to 5, it's going to go from -3 to 7. When you subtract, subtracting shifts to the right, which is a little counterintuitive for some people. One way I think about that, because it's the same if you're, say, drawing a parabola or other kind of figure, is that we're doing things sooner, in a sense. We're allowing things sooner, and so that's actually with addition. How do I say that better? I'll show you another example, and then I'll make more sense of what I just said. So what if I had absolute value of x plus 3 is less than 5? What would be the endpoints there? What would be the range I could have for there? If subtracting shifts to the right, then adding, as we can see, is going to shift to the left. So if normally I'd have 5 and -5, I'm going to want to shift 3 to the left. So I'll be over here at -8 and over here at 2. So if the normal range of just, A is less than 5 kind of thing would be here, what we're going to want is -8 to 2. We're going to want that range. We're shifted 3 to the right. And when I meant about things happening sooner, this is how to explain going to the left, not going to the right, is that if normally we'd start at -5, when we add 3, we get to start sooner because we're adding 3 to our number. So adding shifts to the left. So it may help you to just memorize it. But sometimes I think of it as making sense. I think about, like, what if you were a very precocious child and you did everything 2 years earlier than other people do? So if most people start school at 5 and graduate high school at 18, you're going to start school at 3 and graduate at 16, right? You're doing everything closer to the left because we're adding 2 years to how we treat you. When you're 3, we're treating you like a 5-year-old. When we're 10, we're treating you like a 12-year-old. And when we're 16, we're treating you like an 18-year-old. And you're graduated from high school. So everything starts sooner. Whereas if I subtract, it's like I'm treating you like a younger child. Oh, you don't start school until later and you graduate later. Everything's shifted over to the right. Okay. So Jaideep, you're asking about a quadratic term inside the absolute value. The problem is that that's not going to go on a number line very nicely, because you're getting a quadratic. We can play with it, and certainly if we're not trying to plot x and y, we can think about what the values are. But you'd probably want to work that out algebraically. You'd want to bust the absolute value sign off of your operation and treat it separately. So you'd have something like x squared minus x minus 5 is greater than 0. And you think about the possible values of x there. And then you'd have x squared minus x plus 5 is less than 0. And you'd have to think about those separately. So that would be a pretty heavy duty GMAT problem, to be honest. But you wouldn't do that on you wouldn't plot it very simply on the number line. That would take a little bit more work. Okay. Let's do something different. A lot of us have learned that there are various ways to combine inequalities. And this is another thing that people either do often by picking numbers or by trying to do in their head. And I think there are other ways. So I want to show you something interesting here. We can see two very similar inequalities. I get a plus b is greater than 6. And then when I add c, it's greater than 10. So then my question is c greater than 4? In other words, can I do this? Can I do that? Is this right? Let's test. Let's see. Okay, so number testing, like I said, gets pretty tough on this, but sometimes I have to do it to see if it makes sense. So if a plus b is 6, or sorry, greater than 6, give me a pair of numbers. Give me an a and b. Okay, but give me an a and a b. Let's see. Yeah, so what values do you want to pick? You might not care because we're adding them, but okay. So let's say a is 4 and b is 3. So we know that a plus b is 4 plus 3 is 7. So we know that 7 plus c is greater than 10. So does that make c greater than 4? Seems like c is greater than 3. Uh-oh. I mean, it could be greater than 4. It doesn't tell me no, but it tells me I don't know. Yeah, c might be 3.1. If c is an integer, then it has to be at least 4, although 4 is not itself greater than 4, right? That's another mistake sometimes people, they'll say, oh yeah, it's greater than 3, so it's greater than 4. But wait a minute, that gets out of hand. Next thing you know, you're 100 years old. You'll say, well, I'm greater than 10, so I'm greater than 11. And I'm greater than 11, so I'm greater than 12. No, don't do this, right? So if we know c is greater than 3, we don't even know whether it is 4. And even if it can be 4, we don't know if it's greater than 4. So it looks like we can get a yes or no. But notice even now, we'd have to think about, okay, testing numbers. I could have c be 3.1, or I could have it be 10. So it seems like even with one pair of numbers, I can get a no, and I can get a yes. The danger is, though, what if I pick different numbers that are farther away from 6? For instance, I could perfectly well say, let's see, I'll make a5 and b5. And then I'll say, okay, 10 plus c is greater than 10. I might be tempted to say, oh, all I know is that c is greater than 0. Now, technically, I still could say c is greater than 4 or not. Greater than 0 doesn't tell me if it's greater than 4. But the bigger I get, the more I might not even think about those other values of c, right? Imagine I make a 100 and b 100. Then I'd say, 200 plus c is greater than 10. Now, technically, c is greater than negative 190. Technically, c could still be greater than 4, but it's not the first thing that comes to our mind when we're testing numbers. You might say, oh, it could be negative this, negative that. So what I'm getting at is, obviously, if you really know what's going on with this problem, then picking numbers won't necessarily shake you, and this is fine. But it can be a little overwhelming when you have a lot of different cases to think about. So it can be helpful to have some mechanics, but this mechanic did not work for us. In general, you cannot subtract inequalities. And if you think about why, it may help you a little bit, because you could say, wait a minute, in order to subtract something, I'm really multiplying through by a negative. And if I'm multiplying through by a negative, I'd have to flip the sign. So in fact, sometimes when I'm stacking, whether it's an equation or an inequality, I will actually think about adding negatives instead. You can totally add inequalities, just like you can add equations, as long as you have the sign pointed the same way, right? So if Jaideep has more than $10 and I have more than $10, then you know that together we have more than $20. Doesn't mean we're going to share, right? And it doesn't mean we have close to $20. We could each be billionaires, right? It just tells you that our combined income is, or wealth or whatever, is more than 20. That may or may not be interesting, but we can find it. You can add. So we could add these directly, but then we'd get this, right? We'd get 2a plus 2b plus c is greater than 16. That might not put us any better off than before. However, we could then multiply through by a negative. The problem is when you multiply through by a negative, the sign shifts, and that doesn't really help us much either, right? So this is not, as we saw, sufficient to find the answer. I can't know whether c is greater than 4, and I can prove it by adding well, I'd have less than -6, so I can't even do it, right? So I'd have negative a plus negative b is less than -6, but now I have different signs, so I'd have to do a plus b plus c is greater than 10, and -6 is greater than -a minus b, and this is just terribly unhelpful, right? I'm just going to get a plus b plus c minus 6 is greater than 10 minus a minus b. If I move that over, I'm going to turn into what I had before, which I should. It's the same information. I'm going to get 2a plus 2b plus c is 16. So I can't know this. We don't know. It's inconclusive whether c is greater than 4. You can subtract two inequalities by multiplying through by a negative and stacking. Right? So what I can do to be useful is if I'm given yeah, but notice yeah, so notice what you're doing in your example, Jaideep, is you're having two that are flipping the other way and flipping the sign, and that's what we can do, right? If I know that a plus b is less than 6, right, then I can subtract them. In a sense, I think of it as flipping it around and adding negatives, but you can subtract in that sense. You can say, all right, a plus b plus c is greater than 10, and then I can say negative a minus b is greater than -6. You add these, this is different than what we had before, right? It changed the problem. Now I can say, hey, the a's cancel, the b's cancel, and suddenly I know that c is greater than 4. So the rule is you can add inequalities anytime you like. You just add them directly as long as the signs are facing the same way. You wouldn't want to think about it directly as subtracting, but in a sense you can. If you multiply through by a negative and flip the signs, you can then add them if the signs are now pointing the same way. But if I have two that are both greater than, or two that are both less than, I wouldn't want to think about subtracting them. And generally what I would do, just to make things simpler, is get it in this form. Get it where both signs are pointing the same way, whether it's greater than, less than, I don't care, and think about adding. That way you're less likely to forget, even with equations, right? When I have something like 2x plus y minus 3, and then I'm doing, minus 2x minus y plus 4, I might forget. I might go, okay, yeah, 2x minus 2x, that's good. Y minus y, that's good. No, wait, hold on, it's y minus negative y. So hold on, I actually want 2y, and I want -3 minus 4, so it's -7. So I think, generally speaking, it's better to multiply through that negative. Main takeaway, if you haven't already done this before, is simply that you can stack and add inequalities if the signs are pointing the same way. If you want to cancel something out, get a negative through, but the sign's going to end up switching. Okay, that makes sense? Questions on that? And I would say in a lot of these cases, it's going to be easier to think about that stuff than to sit there going, oh, what could A and B and C be? Especially because it doesn't matter that much what the individual pieces are. In fact, when I asked for values for A plus B, one of you was saying, oh, 7. And I was like, which one? Well, whatever, A plus B is 7. I don't actually care what A and B are individually. So if you're being pretty savvy, you could just say A plus B is 7, and I don't care what A and B are. But sometimes we get hung up on that when we're testing cases. And that's where I think people slow down a lot. And often I'll see people taking a practice exam and their, data sufficiency inequalities problems will be lasting 3 or 4 minutes, which you just can't do. You can't have that time on a test. And it's often because they're trying all these different cases. I think of it as philosophizing. They're sitting there with their coffee and going, what could it be? Instead of just proving what they have. Yeah, and now as far as multiplication and division, you can't do it, right? Multiplication and division you can think about, but you have to interpret, right? So for instance, if I say A is greater than 12 and B is less than 4, even if I flip this and say A is greater than 12 and 4 is greater than B, I don't want to say, hey, 4A is more than 12B. I honestly just don't know, right? I mean, I could think about it. I guess you could say that in a sense, right? You could say, well, at the very, like, let's say B were 4 and A were 12. They can't be, but those are the limits. Then you could say at the very least, then A would be 3 times B. But it starts getting confusing when we think about things like negatives. So I suppose there would be some meaning to saying that that A is greater than 3B. But in a lot of cases, you'll have to think about the limits, especially if you have a dual limit. So for instance, in this case, notice that what if I want to know something about AB, right? So I guess one thing I was getting at is that I can do this, but I'm getting something about A on one side and B on the other. But what if I want to know about AB? Well, what's the biggest that AB can get? If I know that A is more than 12, it seems like there is no limit to that. I know B is less than 4. Do I have an upper limit for AB? It seems like I don't, because let's say, what if A could be 1 million and B is 3? And then if it could be 1 million, why can't it be 2 million, right? So there's no upper limit. What about a lower limit? Is there a lower limit for AB? Kind of the opposite problem there, right? B could be negative, right? So there's no lower limit. So one way or the other, we don't really know very much about the range of AB. It seems like it could be incredibly large or incredibly small, right? It can't be 0, and it can't be, some of the things really close to 0. Actually, that's not even true, right? B is less than 4. So I'm sorry, yeah, B is less than 4. B could be 0, and therefore the whole thing's 0, etc. So yeah, there's no real limit to what this combined thing could be. Sometimes you'll see hard limits if you have a dual-sided one. So imagine that I've got something like -5 is less than x is less than 4. And let's say I've got something like this. -12 is less than y is less than 2. And I might want to think about what the range of x, y could be. So what's ignoring the less than part, just, what's the upper limit for x, y? A natural temptation is to say 8. And some of you may be watching this saying 8. 8 is actually much smaller than the upper limit of x, y. Can anyone see why? It's true that the biggest x can approach is 4. It can be almost 4, 3.99, whatever. Y can be almost 2, and that puts us at 8. But there's a way to get a bigger xy value. Yeah, what if I were to combine my negatives? So I have to interpret on these, and I can't do it too automatically because it depends. Do I automatically include the negatives, the bottom, the top? It depends on what the range looks like. So in this case, I have to think about what would maximize x, y, and it's going to be multiplying x times the bottom ends of x and y to get 60. So then the lower, I'd want to think about how do I make it as negative as possible. I could take the smallest negative value I can get is here. And the largest positive value I can get is here. So I would have negative 48. You might have cases where you have to pull differently and make a trade-off. Like what if you had negative 5 here and negative 12 up here? You might have to say, well, okay, if I make x negative 12, that limits y to 2, that's negative 24. Whereas if I make y negative 5, oh, that combines with a bigger x, but that's still just negative 20. Okay, I'd want still 12 and 2 if I flip those. So you have to think about which combo you want, but you can't pull from the same thing. I can't do, let's say 12 and 2 because they're the same variable, right? So usually I'd want a very big number on one side or the other, but I want the biggest combo I can. So 12 and 4 is more than 5 and 2. Okay. So watch those ends when you have to interpret. Okay, questions about any of that? Let's try another couple moves. One thing that they'll deal with a lot is, with number properties, when you're thinking about greater than or less than 0, do I know if things are positive or negative? And sometimes they trick us into thinking that we have to think about a lot of positive negative cases when maybe we really don't. So here's one. This is a full data sufficiency. So I'll let you pull this one in. If you're new to data sufficiency, I'll type what those mean up on the screen. But I think most of the folks here said they were pros, but if you're watching at home, I'll just make sure we know what these mean while people are looking at this. So take a moment to try it. Okay, if you're not sure, put in your best shot. Give it a guess. If you're watching the video, write down a guess so you're committed to it. Okay. So a little bit of sneakiness here, right? Now, no one who polled in said that statement was sufficient. Good. It's designed to coerce you into saying that it is, isn't it? Right? What they're hoping, again, when they write this, I guess I should say what I'm hoping I wrote this, but what they might try to be bullying you into is just say, hey, multiply both sides by b, and I get a is less than b. What's the problem with this? We don't know the sign of b, so we don't know whether to flip the sign. So it's a is less than b, right? If b is positive, right? Or if B is negative, A is greater than B, right? If B is negative. Okay, so when we write down our AD, BCE, if you haven't learned that yet, it's one of the most valuable things for data sufficiency. If statement 1 is insufficient, we cross off AD. Now, statement 2 gets us a lot closer. It's tantalizing. And although it doesn't end up being sufficient, if the question were slightly different, it would be, right? What can I do with statement 2? Notice that I know the sign of 12, thankfully. So I can multiply by 12 just fine. And the beautiful thing, when you multiply something over to the other side, when it's 0, then the whole thing is just 0. So I'll get 7a minus 14b is less than 0. I can also divide 3 by 7. And if the question were just slightly different, this would be sufficient. Because what I can find is that a is less than 2b. And I hope you saw that. If you saw that and said, hey, that doesn't mean a is less than b, that's absolutely right. Absolutely right. I don't know, because 2b is, presumably, if they're positive, bigger than b. If they're negative, it's less, right? So it again would may or may not be useful, even if we knew the sign. But it's getting us much closer, right? So this is insufficient, but it would give us the answer to that if that's what we're looking for. So then I try to put these together, and I know that a is less than b, and I know that a is less than 2b, but okay, that's not really very helpful. So now I'm just saying, if b is positive, then a is less than b, which is less than 2b. If b is negative, then a is greater than b. But I also know that if b is negative, b is going to be bigger than 2b. But that's still, wait, a is less than 2b. So this can't be. So it tells me it's this one. Have I proven that C is the answer? What do you think? So we have to think about those cases, right? It seems like maybe yes, it's a little sneaky, right? So if A is less than 2B and also less than B, that's what you'd see when it's positive, right? Now we didn't prove that A is less than B. We proved that it's one or the other. Either A is less than B or A is greater than B. The nice thing about the A is less than 2B though is it didn't depend on the sign. We just proved that outright. A is less than 2B A minus 2B is less than 0. So A is less than 2B. So we know this part's true. The question is B itself greater than or less than A? But if B is positive, then 2B is bigger than B. Okay. The problem is, so if B is positive, could it be this? What do you think? Could I have that? Well, it can't be 2B is less than B if B is positive, right? 2 times the number can't be. So I could think about this, but hold on, would that fit that A over B is less than 1? Right? If A is greater than B, then that first statement wouldn't work. So I actually have to cut this. We can actually prove C here, right? Because what this does sneakily is it eliminates one of our 2 cases, right? We have 2 cases here, right? So if we kind of, here, let me clear this a little bit, right? If we look at this as, hey, A is greater than B or A is less than B, right? What is the sign? And then if we look at this one and say, hey, A is less than 2B, but is it less than B, right? Then we can say, all right, does this narrow down the sign when we put them together, right? If B is positive, then B should be less than 2B. And so if B is positive, A is also less than B. If B is negative, then 2B should be less than B, and that contradicts this case. And that's why together they're sufficient. If everything is negative, JD, notice that A's sign doesn't affect anything, right? A can be negative or positive, we don't care. But if we multiply through both sides by B, we get A is less than B directly, right? And in the second, we get A less than 2B. So the sign of A doesn't end up affecting things. We have it here, right? If we know that A is less than 2B, we're only trying to figure out if it's less than B. We know that A is either greater than B or less than B. They're not the same, and that it depends on the sign. But if B were negative, where we flip the sign where A is less than B, then we would have 2B is less than B, right? But then we'd have A on the other side. Do you see that? Little sneaky. So lots to watch with these. We can think about a lot of cases, but sometimes it's better to think about positive and negative than to think about actually picking integers. Sure, question? I think you just have to type. I don't think it'll let you on. So feel free to type if you have a question on that. If B is negative, but A is positive. But in that case, then A wouldn't be less than 2B. Yeah, so we can't have that case, right? Remember that A must be less than 2B because statement 2 says that it is. And that's where their constraint comes in. Okay. All right, I'm going to stop there. Thanks so much, everyone, for coming. I feel like I could talk about inequalities for another hour or two, so maybe we'll do another of these sometime. But definitely check us out. If you want to see any of our other resources, look up any of our other free YouTube courses, anything else. Hope everyone enjoyed. Stick around if you have other questions. Other than that, best of luck with your studies. Thanks.